In today's episode, Venkat Kirishnamurthy takes us into the ins and outs of designing an AI data center.
Let's take 32 GPUs. That's on 4 servers. All of them are running at 400 gig.
He shows us such a data center is not just about piling up expensive GPUs.
So why are the drops happening? Am I running out of bandwidth? Am I having errors on the hardware? What is the errors due to? So those are the things that we validate before we hand the customer the infrastructure.
And takes us through the techniques to deploy such a data center in how many weeks?
There were like 128 servers and we had a 3-4 days to bring the whole thing up.
Welcome to Cisco Tech Stories, a podcast with real-life stories from real-life engineers. Your hosts are Nicholas and Tristan.
Hey everyone, and welcome back to another episode of the Cisco Tech Stories. I'm Nico.
And I'm Tristan. If you're like us, you can go a day without hearing about AI. It's everywhere, right? In your phone, in your car, in your coffee maker, or maybe not that one, or at least not yet.
Not yet, okay. But let's be real. So much of what we hear about AI is just marketing buzz. It sounds great, but what is actually happening behind the scenes?
Today, we are pulling back the curtain. We are talking to the folks who just don't talk about AI, they deploy it. The ones building the data center that make this all possible.
That's right. Joining us today is Venkat Kirishnamurthy, a principal architect here at Cisco who's out there, boots on the ground, helping our customers design and launch real-world AI data centers. No fluff, just the reality of what it takes to power the next generation of technology.
So, if you want to go beyond the headlines and find out how AI is really built, stick around, let's get into it.
Hello, Venkat. Thanks, Nico. Thanks, Tristan. Nice to be on this podcast.
Before we start talking about data centers, can you introduce yourself in a few minutes? What's your career path, Venkat?
I'm a principal architect with the CX product management team. I've been in Cisco for a long time, probably close to about 27 years. I started my career at a small company in India where I was building PCs from scratch, basically lining up various cards, various CPUs, and so many things that I was doing. Another thing that I also did was I then started getting interested in the compute side of the house, where I was building computers, building operating systems. I was one of the first guys in India to build the whole Linux into a company's distribution for a company, where we used Slackware to build video-based desktops with higher resolutions at 1080p. I worked for Sun Microsystems in the US for about a year before I joined Cisco Systems as a system administrator. My first role was basically administering Linux and Sun Microsystem servers. Then I started looking after HP servers, and then I eventually started looking into storage subsystems. Basically, we're looking at EMC, NAS, and the Sun storage portfolio. At some point of time, then I had an opportunity to start working with the Cisco MDS switches right from the days it was being built. And that allowed me to get exposure into the storage area network, and at which point I switched into services. And I have been in services ever since sometime 2002 was a time period when I joined the services, and I have been working on different technologies. I did do storage area networks for a while. Then I got pulled into doing pure networking with the Nexus 9K, Nexus 7K portfolio. Then I also did a whole bunch of work on the compute side of the house when Cisco introduced the UCS platform. Then I did a lot of work with the hyperconverged infrastructure, which was the Cisco's HyperFlex platform, where we brought it to market and we rolled it out and enabled theaters to do work on that and the field to deploy it on the ground. The next thing that I did after doing hyperconverged infrastructure was doing data center networking, which is VXLAN EVPN. With the Nexus dashboard platform. And I did this for about 5 years, at which point we were asked to talk about, hey, we have AI infrastructure coming up. We need people with compute, storage, and networking, which was a perfect fit. So I transitioned into dealing with all things AI in the data centers, at which point we had to build a whole practice that allows us to go deploy the AI infrastructure for Cisco's customers. As a part of this profile, I had to create and train the field engineers so that they're able to go deal with customers. I think it's a long-winded answer, but that's my background in short.
If I can get straight into it, I mean, you mentioned your current role is with the AI data center.
where do we start when we get into AI data center?
So when we look at AI data center, right, the word AI data center represents a lot. One of the key things that we talk about when we go into AI data centers is, do I have the infrastructure that is ready? When I talk about infrastructure, it's just not one piece of the data center. We are talking about networking. We're talking about compute. We're talking about GPUs in the compute. We're talking about specialized storage. And then we start going into the interesting topics of how all these elements that I just spoke about come together with the operating system that sits on top of the compute. Another key element that we also need to consider is, once I have loaded the operating system and the drivers for the GPUs and configured my networks to do what it needs to do in terms of backend networking and front-end networking, I also need to think about, how do I load applications on top of it? Essentially, now we are starting to talk about, do I want to do training infrastructure? Do I want to do inferencing infrastructure? So what does it mean? In the training infrastructure, I need to worry about huge amounts of data that has to be downloaded into the compute. And I also need to worry about how the GPUs that are in these servers are able to communicate with each other. And how do I configure the networking to make sure that I have a lossless infrastructure? That's one key part of it. On the other hand, if I'm going to do inferencing, I start thinking about, do I have enough bandwidth to support customers who are going to use my inferencing models that I load onto my GPU servers? And how many tokens do I need? What is the time to first token? What are the things that I need to worry about when I make this available as a web application that customers can start asking? The typical things that you would think about inferencing is chatbots. You would start asking questions like all of us have dealt with ChatGPT or Gemini or Perplexity. So these are some of the top line chatbots that we think about. And if I were to build a chatbot in my data center, what would I need to do? So these are all the considerations that I would have to take into account when I start talking to a customer about AI data center.
I just want to take a second to clarify one difference between the two things you just covered. Correct me if I'm wrong, Venkat, but inferencing is basically when you download an existing model, a publicly existing model that was already trained on internet data, and you run it against your queries or your data, and you want to keep that private. So it allows to keep the data local and not require a paid subscription to a cloud service. While training is when you take a base model and you train it yourself from scratch with your data. So it's not trained with internet data, but it gets specialized about your data and better at it than the public models are. Is that correct?
That's correct, Nico. Very good point. Very good distinction. So when I start looking at inferencing, right, I can use ready-made models. So you have different places on the internet where you can get the models. The question comes is, when you get a model that has been trained by somebody else. It doesn't have your data. So there are two ways to look at it. You can either take the model and use whatever training it has been put through and use that for your general queries. For example, if I were Cisco, or if I were a company that is trying to make the data more relevant to me, then the model has to go through a process called fine-tuning. Okay. Essentially, what you do is you take data that you have that is proprietary to your company. And because the model is local to your data center, its data is not going out, you can feed the model a lot of data. And then you can tell, hey, I want you to fine-tune based on the data I'm providing you. Basically, what it does is the model then absorbs the data, trains it, and when you start asking questions, it gives you more specific answers to the data that you've trained it on. Okay, that is the advantage of having local. Like you correctly said, there is no need to do external subscription. A model is yours. You just train it and use it. And the second part of it is when we start talking about training models. I have a whole bunch of data, and I don't want to use my existing models to do any of that. I want to create a model from scratch that only contains my data. Say, for example, if Cisco were to do it, hypothetically, we could take all the customer data that we have from TAC and the solutions we have, feed it, use that, and train a whole new model that is specific to only Cisco data. It does not have any external knowledge, which is great for troubleshooting. And that's something similar to what we're doing with AI Canvas from Cisco. So it's those kind of applications that require a large amount of GPUs that takes a whole bunch of data and trains them and creates a model for you.
So that's in the training scenario that you need a lot of storage in your data center, right? You need to have a massive amount of data to be able to properly train the AI. That's why we need so much storage.
That is correct. So it depends on the volume of data, because Cisco has been in existence for about 30 plus years. So we have so much TAG data that you could just take a lot of storage you would need dump it into the storage, then load it into the GPUs, and the GPUs do the training and they dump it back into the disk as a model. So you would need a lot of space, which is where you look into the storage component of the infrastructure. And the storage component comes with different options. You can either use traditional storage, which is mostly like NFS-based storage, but more newer storages are coming up where you have like a distributed storage ecosystem. That means the storage is distributed. And plus, the newer storages can also do something called any protocol over RDMA. So this is another important concept that comes into the whole planning ecosystem when we start doing AI data center. This one is called the RDMA. It is remote direct memory access. So the idea about doing this is, why do I need RDMA? I need RDMA because when a system does I/O in a traditional compute environment, the I/O is always gated by the CPU. Every I/O operations, the CPU is interrupted and the CPU then sends, okay, you can do the I/O, then the I/O completes itself. But what happens is when you're really doing training models and you're feeding a large amount of data, if the compute or the CPU is going to interrupt every I/O operations, I'm going to get very, very slow performance. So RDMA allows you a mechanism wherein it can completely isolate the CPU for the I/O path. Because I have 400 gig NICs or 800 gigs NICs on my compute platform, they can now use the 400 gig without bothering about the CPU. So this gives you a really, really high throughput that allows you to transfer memory between the NICs and the memory subsystems without touching the CPU, which means you're going to get line rate speed. When you do enough of these data centers and enough of these deployments, you see that every time you have, typically the servers that we have about 8 400 gig NICs for the backend. We can see all of them pumping out 400 gigs of data at the same time. And that is why it becomes more critical that we are able to support RDMA that allows us to do direct memory to memory transfer without bypassing the CPU.
I guess the idea is that these compute servers / GPU cost so much to purchase and to operate in terms of electricity that customers don't want anything slowing them down in order to make the most of it, right?
That is correct. Again, a very key point, Nico. So customers are paying a lot of money for the GPUs. And they don't want the GPUs to sit idle. If I were to go through the CPU, I'm waiting for the CPU to give me permissions for the GPU to function, which is what we don't want. So we want the load and the transformation of the data independent of the CPU, which is why this is very, very important in most AI data centers.
And if we come back on the networking side, I mean, you mentioned one single server can have 400 G NICs, even 800 gig NICs. If you multiply that by the amount of servers, that will give you terabytes per second of data that you need to handle. So what are the constraints that happen on the networking part of the whole thing?
So typically, if you look at the UCS 885 servers, they have 8 GPUs, okay? It can be H200s, H100s, B300, it could be AMD, MI350s, 300s, whatever the GPU is. Each of the GPU typically has a one NIC associated to it. So if I have 8 GPUs on a server, which is what you can get with, you cannot get any less, you're going to have 8 400 gig NICs. So you're talking about 3.2 terabits per second that the server can pump out. So what happens in AI/ML data centers is we start now going through the process of figuring out how best to configure the infrastructure. So in this case, what we do is we start separating out the networks. What do I mean by that? I am going to separate out the front-end network from the back-end network from the storage network. So on very large, high-performance data centers, you're going to see 3 different networks. So now let's go into each one of them. The most important network that we're going to talk about with respect to GPU is the backend network. This backend network, yes, again, we have different flavors of protocols that we can use. Typically, by and large, all of them will have to be lossless. They have to support something called the RoCE, which is RDMA over converged Ethernet. They have to support something called the priority flow control and end-to-end congestion notification. These are the very basic qualifications that are required. And it's almost imperative that we are going to use a clause fabric, which is a spine leaf architecture for the backend for most places. We can also have a leaf-only configurations, but typically you see for large networks, you will see a spine leaf architecture. And most of these switches either operate at 800 gigs or 400 gigs. Okay. Usually you'll see the spines at 800 gigs. You'll see the leaf at 400 gigs. The only reason the leaves are at 400 gigs is right now, we don't have a NIC card that does 800 gig in a single port. It probably has 2 ports, which can do 400 each. So you're okay with 400 gigs on the leaves. And the nice part about this was this is independent of everything else. The only thing that the backend network lives for is to support the GPUs transferring a ton of data. And why do I need this? When you look at the GPUs, what is the primary functions of the GPU? The primary functions of the GPU is to take all your data, compute it, and they use something called collective communications. And this is something called, you would have heard about all reduce, all to all, any to any kind of a communications. That means it is basically talking about what kind of computations they will do. When you supply data to a GPU cluster, the data is going to be split up into small chunks, and every GPU is going to get a piece of the data. When the GPU gets a piece of the data, they're going to compute the information, and they're going to come up with a solution of the data that they see. Then all the data needs to be exchanged between all the GPUs. When you do this, what happens is we are going to see the network completely flooded at this point of time.
And I suppose they transfer all their data exactly at the same time, right?
They do at the same time, exactly right. So that is why we need a completely lossless fabric that can support this kinds of speeds. And what we want to do is we want to have the best possible network for the backend, so the data is transmitted as quickly as possible. And the fact of the matter is my GPU is waiting for the smallest duration before they can restart computing. So that is why we see the requirements for specialized backend network for training infrastructure in general. The second thing that we want to do is the front-end network. The front-end network is a traditional data center network, except in the world of AI, it needs to be looked at specifically, because when I start having something like an inference engine, say, for example, all of you, I don't know how many of us are aware, all of us have used Circuit, right?
Nico here. Small note for our listeners. Here, Venkat talks about something called Circuit. This is simply the name of the internal AI we have at Cisco. We're not allowed to use public AIs to ask our random everyday question, which could contain sensitive data. And therefore, we have an internal AI chatbot called Circuit. Now, back to the episode with this small bit of information.
We are about, 70,000 employees at Cisco? Everybody could be hitting Circuit at the same time. I need to make sure that I have enough bandwidth going to the model that I'm able to support 70,000 employees using the instance. Why does this matter? For example, if you were into ChatGPT and you type a question and it comes back after an hour, you would probably lose interest in that. So it becomes very critical to have a responsive front-end network infrastructure that allows people to interact with it frequently and use it. That's one of the key elements that we need to look when we start looking at the front-end architecture. So typically, when I go into a customer, I start asking the questions, hey, you are looking to do an inferencing model. Hey, do you have at least 100 gig of throughput to the server? Does your front-end network support all these capabilities? If not, we need to start looking at how we can upgrade your front-end network to make sure it works. And the last but not the least is a critical data point is the storage infrastructure. When you talk about storage infrastructure, right, again, the same principles apply, because now think about training, right? I could potentially have multiple petabytes of data that I need to train. I need to get them into the GPU cluster as quickly as possible. How do I do this? I need something like RDMA protocol that is running in the background that will allow storage to run over the RDMA. Okay, so you will have protocols like NFS over RDMA, you're going to have iSCSI over RDMA, or you're going to have NVMe over RDMA. So all of this allows you to get the fastest possible path of the data from the storage to the compute. And another thing that's going to happen is when you do a training job, right? Everybody feeds the data. And let's say after about 30 days, you have a lot of data, so it takes about 30 days to create a model. At the end of the 30 days, I want to be able to save the data somewhere else and then create a model, then start on my next set of training with new parameters. So if you look at how training works, right? I get a whole bunch of data. I start training on it. And the idea is if I have a huge volume of data and I do training, I'm going to do training in phases. This is called checkpointing in training infrastructure. As I do partial amounts of training, I checkpoint my trained data into the storage so that I can go back to that point in time copy. Why do I need this? If my job is running for 30 days or 40 days, if you look at all the ChatGPT models that they train, some of them take as long as 96 days. If at any point of time, if my infrastructure fails for whatever reason, right, I have to start from zero. So there is a point called checkpointing that we do as frequently as possible so that I can get back to the nearest data so I don't have to start from day zero. So think about a situation where I'm on day 95 of a 96-day training and everything fails. I don't want to start from day zero. So for that, I need super fast disks. So that is why storage is playing a lot more key role. And we need to worry about storage when we're dealing with large complex clusters.
But excuse my layman's knowledge of storage networking, right? But isn't storage always going to be a bottleneck compared to GPUs? Fast NVMe storage is still order of magnitude slower than GPUs. Am I correct, or am I missing something?
To an extent, yes, but that is where we start seeing vendors go into something called a distributed storage, which is pretty close to this one. So they have a ton of cache sitting on the storage. So I'm not really waiting for the writes to happen to the disk, which happens behind the scenes. I write it into my cache, and the cache takes care of pushing it down to the disks.
The cache is RAM, basically, right?
The cache is basically RAM. So
Yeah.
Again, how do I protect against one system failing? I write the data to multiple nodes. So even if one node fails, I still have access to the data that I don't lose it. Of course, if I lose all my nodes in the storage cluster, I'm lost. Typically, that doesn't happen. You cannot design for n failures. So you do n plus 1, n plus 2, n plus 3. So we take care of it with n plus 3 here.
Basically, the idea of this storage is that you have a gigantic pool of hard drives, and it doesn't matter if they're SSD, NVMe, or whatever. It's a big pile of cache to accelerate it in front. But all of that doesn't matter because the GPUs don't care about any of this, right? They just have access to a huge data lake, and they write and read to it, and they don't care about any of the details.
That's correct. Yeah. And the nice thing about this storage aspect is the GPU would be able to ask for a specific data directly from the storage. So that's what RDMA allows you to do, a lot of things. So if the GPU is programmed in the right way, it can say, hey, go fetch this data for me. And it can go to the disks and get it directly without the CPU being in the way.
I actually want to come back to something you said. You mentioned a customer who had a data center using both NVIDIA and AMD. That seems a bit unusual, right? Because these two main brands have different API, if that's the proper name, right? AMD has ROCm and NVIDIA has CUDA, and they work slightly differently. So it's not trivial to use both of them. What's the rationale behind this, behind using both brands? Is it availability? Is it price?
I think it depends on the customer that we were working with. Multiple customers we were working with, they each have a different goal in mind. So one of the customers that I was doing GPU as a service where we deployed about 1,000 GPUs. Roughly about 2/3 of it was NVIDIA, the other 1/3 was AMD. The customer was looking to evaluate both in terms of how flexible they are. In one of the cases, the customer was using the AMD GPUs to do inferencing. That was a primary goal that they were looking at. So they went ahead and said, okay, let me do this and let me try it out for inferencing. But as we were going through the configuration, the customer changed their mind. They said, hey, I just don't want a particular CPU to do inferencing. I want it to be able to do training too. When we start looking at how we go about doing this leads to an interesting situation where we have a set of backend infrastructure that we configured for training infrastructures. And we had a backend infrastructure. We didn't have a backend infrastructure for inferencing because you don't need that. We were using more in terms of KVM to virtualize the GPUs so that the customers could pick 1, 2, 4, or 8 GPUs and run their inferencing on that particular system. On the training mode, the customer had to pick something of the order of 8 GPUs in a server. They could pick up multiple servers. If they picked up 3 servers, they would get 24 GPUs, so on and so forth. The key element that we had to deal with was from a networking perspective, how do you make this all work seamlessly? So for that, what we did was we use VXLAN EVPN as the backbone for the infrastructure, where we were able to provide multi-tenancy for multiple customers to use the same infrastructure across the same network. So what is the functionalities? When we need multi-tenancy, all of the GPUs are sitting in the same L2 network. That's how it was designed. We had to put boundaries around the layers, put a separate VRF, put a separate VNI within that same infrastructure that will allow us to segregate multiple GPUs based on what the customer's tenant required. And the easiest way to do it was using VXLAN EVPN that allows us to give the construct of multi-tenancy. It's built into it. So it was an easy win for us. We were able to tune the networks individually for each customer's use.
Hearing you, it's obvious that using an ACI fabric is a clear advantage in terms of deployment and micro-segmentation for this kind of data center. But it seems even more true for expensive GPUs where the company want to share GPU time across different training projects, across different departments. It sounds like the kind of expensive structure you want to sub-rent, if that exists, right? To provide as a service internally to maximize the ROI, because it's not just one team, one department using it. You have one cost infrastructure that you want to share between different teams and departments that may have different needs of it. You might not always be doing training, so you might want to reuse the resources for other stuff. So I guess it makes the ACI fabric a no-brainer for this, right? Compared to old school networking. I think that would just not do the job right.
That is correct. That is very, very key important, especially for this customer as a service provider customer. And they were looking to do GPU as a service to extend to their customers. So we had to make sure that we had an airtight configuration so customers don't see each other's data and we still get the segregation and security that the customer is looking for. And the easiest way to do it was VXLAN EVPN. I've also had supported customers who have done the opposite of this. They said, I'm the only consumer of the data, only consumer of the infrastructure. I want all the GPUs in a single domain. So in those situations, what we have done is we said, okay, instead of doing VXLAN L2 networks, we are going to do a routed eBGP fabric, and every GPU can talk to every GPU within the infrastructure. So this was another customer who was using 1024 GPUs all in a single fabric.
You mentioned 1,000 GPU. It's actually a couple of times that you mentioned 1,000 GPUs. Is that the scale of the data centers, AI data centers that we are dealing with nowadays, or is this much smaller or bigger?
Actually, we are seeing a lot of customers. Many of the customers that I've spoken about are from a service provider background who are doing GPU as a service. We are also looking at enterprises. They probably start out at 256 GPUs, but if you look at some of the customers, if you look at the 2-year plan, they're looking to scale all the way up to 1,000 GPUs or 2,000 GPUs. Most of the service providers that we have dealt with, they start off at 1,000 GPUs, but we have seen customers who are at 65,000 GPUs, 256,000 GPUs. So from a service provider perspective, I think most of the enterprises would start small, but they would eventually, depending upon what they use it for and how the usage grows, they would probably scale out. But most of the service providers start at 1,000 at the minimum. Some of them we are seeing almost up to 8,000 GPUs. Some of them are talking about 25,000 GPUs, so on and so forth. Yeah.
So when you say 1,000, let's say 1,000 GPU, you mentioned servers now they support 8 GPUs each, so that's still over 100 servers, right?
Yep.
This is the calculation. Okay.
That's a calculation.
So that's 1 port per GPU. So that gives you 8 ports per server. And that gives you how many switch you need for that to be
that's correct.
Switch port.
So if you think about it, when you look at a server, right, the server typically is going to have 8 NICs for 8 GPUs. It is going to have 2 additional NICs which are 2-port NICs, which are for something called the front end, which we connect to the front end network, and 2 more ports that connect to the back of storage network. So typically, if you look at this, just for the back-end network infrastructure, depending upon if you have 1,024 GPUs, I need 1,024 ports at the leaf layer. So the back-end network starts scaling pretty fast. They start becoming pretty big, and we need to make sure that everything works right and everything is tuned. Another key element that I didn't speak a lot about is it is just not about connecting the servers and the switches together and the storage together. There is a lot of know-how that goes into actually tuning the fabric. So when we go start using Cisco switches, some of the switches, we have the way to tune the buffers in the switch. How do we tune something called priority flow control that I spoke about, and end-to-end congestion notification? And we also have something called dynamic load balancing. We need to tune all of this for the fabric to run harmoniously so that we get the maximum throughput. Let me step back a little bit on the networking side, then I'll come back to the compute side. On the networking side, when you start transmitting data, right, when you have a spine leaf configuration, we know something called ECMP, equal cost multipathing. Okay. The equal cost multipathing is a way for us to have no single point of failure in the path, but we also have a downside to it. The downside is we depend on entropy to get uniform utilization of the links in a data center. When you're doing non-AI traffic, it's not a big deal. Your average utilization is about 5-10% with a peak of about 30%. Now, when I start dealing with AI infrastructure, I'm pegged at 100% all the time. And I need my load balancing on my spine and the leaf layer to be flawless. Yeah. So how do I accomplish this? The regular ECMP is not going to work, but what I end up doing is we need to start looking at something called user-defined field that gives us a little more entropy, because when you do ECMP, you have the 5 tuple, which is the source IP, destination IP, source port, destination port, and the protocol. Those are the 5 tuples we use. But that's not enough, because when you start IP addressing my servers, it's 10.1.1.1, 10.1.1.1.2, so on and so forth. So there is no entropy within the IP address. So I don't get diversity of path. In order to do that, we introduce something called the dynamic load balancing. The dynamic load balancing, instead of looking at a single flow, it breaks down the flow into flowlets, smaller flows, subflows. And each flow can take an autonomous path or a unique path in the fabric, which will allow me to get a better utilization, much, much better, almost close to about 90-95% utilization on all my links, which means I keep all my links that I have connected completely saturated. So that allows me to bring up the performance of the fabric. So we need to tune that. Another thing that we also need to tune is the Rocky, PFC, and ECN, which are also critical. We have certain leverages to tune that allows us to optimize performance better. Having done that, we also talk about when we say, now that the network is finely tuned, what do I need to tune on the server side? The server side allows us certain leeways because it's the NVIDIA stack or the AMD stack. We tune the appropriate variables that allows us to do diversity of path, even in the server itself. So we have something called the Q pairs, which is an InfiniBand term, which allows us to separate out the Q pairs uniquely at the source. We add the Q pairs diversity and the dynamic load balancing, we can get close to about 95% uniform utilization of the links between the leaves and the spine. And this gives us about 390 gigs on a 400 gig link, which is the max, because the rest, 390, another 8 gigs goes away in headers and all the other stuff. Yeah, we're pretty much close to, yeah.
Close enough.
Okay, I don't know if this question is stupid or not, but coming from the enterprise world, I'm wondering, to reach this near zero loss, are you using quality of service in the data center fabric?
We do use quality of service. So that's why I'm going back to, go back to when I was talking about Nexus dashboard and Nexus fabric controller and how we use that to configure the backend infrastructure or the front-end infrastructure. We have specific QoS templates that we have predefined that you can pull in. That will ensure that the QoS is uniformly configured and correctly configured based on the speeds you're using. So what we've seen in the field is some of the customers have 100 gig switches, some of the customers only have 200 gig, some of them have 400 gig. So based on the speeds that you have, we have predefined various QoS parameters that gets automatically implemented for you in the fabric. It's no longer a matter of you guessing to figure out what is the right level of QoS. It's already done for you. What we can do is we actually go back in based on the workload the customer is putting on the servers and the network. We can fine tune it further. By default, you get a good set of baseline to start with, from which you can tune to get better performance based on what the customer is putting on the infrastructure.
How do you actually measure that the impact of the QoS or the settings that you're doing on your network? So do you have like a benchmarking tool, or do you need to run a full AI production setup to measure that it works correctly?
So what we normally do as a part of our deployment service is we use a combination of tools. If you use the NVIDIA Collective Communications Library, it's called the NICL. When you use the AMD Collective Communications Library, it's called the RICL. RICL stands for ROCm Collective Communications Library. So depending upon which GPU platform you're deploying, we use these two tests to validate all the throughput. This allows us to test the validation of the throughput right from the host, from the GPU into the network and back to the other GPU. We test latency, we test throughputs, we test all of this. And that is part and parcel of every deployment we do. We hand over a document to the customer saying that, hey, here you go. This is what we saw on your network. This is pretty close to what we have tested and what is published online. And there we stop there. Now, if the customer has their own unique workload, in many cases, many customers give us a model script of what they expect their workload to look like. We run that on the infrastructure, and that's where we start doing the fine tuning. We have done enough number of customers, so we know what the baseline is going to look like, and that is what we go apply to every single customers we deploy. Now, if the customer gives me a unique test workload, we run the test workload, then we see what we can tune to make the job completion time. That's another keywords that you'll be hearing about when you do AI/ML. So job completion time measures how quickly the job can complete. That means it's basically measuring how long the GPU is running, how long the network is in use, and how quickly it can come off the network back to the GPU. They call it a job completion time. There are a lot of things that go into measuring a job completion time. And our main goal in many of the training infrastructure that we stand up is, as we tune the infrastructure, we want to get the lowest possible job completion time with least amount of errors. And that's our goal. And that's how we do it. If the customer does not have a workload, we just run the nickel test to validate that we're getting about 392 to 392 gigabits per second. And we stop there.
You mentioned errors. What would be considered an error in an AI data center?
Again, the amount of data we are pumping, right? Say, for example, let's take 32 GPUs. That's on 4 servers. All of them are running at 400 gig.
Right.
The things that I'm looking for uniquely are, how many drops do I have? Is the drops affecting my job completion time? If there are drops, why are the drops happening? Am I running out of bandwidth? Am I having errors on the hardware? What is the errors due to? So those are the things that we validate before we hand the customer the infrastructure. And those are the things that we need to look at and make sure that everything is clean and error-free.
And actually, that gives me another question in mind. So this is what you do before to hand over the keys to the customer. But what's happening after? So how do you actually monitor an AI data center infrastructure like this? What tools do we use? What method do you use?
What we have is, we have tied up with our Splunk partners. So we have something called the ITSM-based AI ML infrastructure monitoring toolkit. So it's a dashboard that can look at your network, your compute, your GPUs, and your storage infrastructure performance. And we can give you a dashboard of what is happening with where, and people can start looking at it. It can start predicting certain amount of things, because all the data, it gets transmitted to a Splunk data store, and then this is built on the Splunk. So we do have equipment. And another key element of this is, because all of this is running at 400 gigs, we need to have a lot of data points, a lot of data store, and accurate measurement that will allow us to look at things over a period of time and correctly predict what is going to happen. So there are enough intelligence in this whole process where we can actually look at things and predict what is going to happen in your network based on what we're seeing from a pattern. So all that is being built and that's available. And yeah, we can do all of that stuff.
I suppose when you deploy such a data center, you don't deploy servers one by one, right? You don't do that manually. You must have a method to deploy at scale. And then that brings the question about maintenance. How do you run firmware updates? How do you upgrade the stuff? What are the methods used?
It's a real problem. When we did one of the first large implementation of 1,000 GPUs, of course, there were like 128 servers, and we had a 3-4 days to bring the whole thing up. So what we did was, we started looking at Pixie Boot and a way to automate this one from a large scale. So essentially, we wanted something that is zero touch provisioning, but it's not quite zero. It's 99% zero touch provisioning. You just have to select a NIC card. You just have to select a NIC card that you're going to boot with. We have close to about 15 NICs on this box. Every box has 15 NICs. So I had to pick the right NIC to Pixie Boot, which is authorized by its MAC address. So we had to set up a whole bunch of automation that allowed us to install the operating system, load the drivers on top of it, and also patch the system to what level we wanted it to be patched. So all of this, so long story short, we were able to get the automation up and running, and we were able to provision 128 boxes in 2 days.
Pretty respectable. It's pretty good.
Yeah.
And for the maintenance part, how does that work? I mean,
the maintenance part is going to be pretty tricky, because what happens by and large is, the ecosystem of drivers for an AI infrastructure is pretty delicate. People don't normally upgrade every 2 months. The OS can be upgraded, but the driver stack is still the static. So there are 2 ways to do the upgrades. We allow the customer to upgrade the operating system in conjunction with the drivers, because they go hand in hand. What happens is, some of the drivers that the vendors, NVIDIA and AMD, publish are tied to a particular kernel version. If I go beyond the kernel version, they won't work. So we have to be very careful when we upgrade this. And there is a process that we have devised where we keep the kernel version static, and we only upgrade packages as required that are supported with that particular kernel version.
I imagine this must be a very fast pacing environment. When I see the driver update for my GPU for gaming at home, it's like a new driver like every week, if not more. how does a customer decide to choose a particular kernel and driver version to make sure that it's stable with the workload that they need? It must be crazy, right?
Yeah, it is crazy. So typically, most of the short answer to this, they don't upgrade. Customers get onto a server
Okay.
version unless they see issues. They don't touch the stack. They leave it as it is. And when they get a new set of servers, then they look at upgrading those because it's a whole
Okay.
new pod that they can upgrade without disrupting the existing pod. Because think about it in a very simple terms, right? Some of the large scale hyperscalers, they are running a million GPUs. They're not a single monolithic fabric, but they are smaller chunks of 256 GPUs or 1000 GPUs or 8000 GPUs. And they are running, some of them are running really old firmware, as old as 2, 3 years ago. What they do is when the GPUs fall off, they just put new GPUs and add new firmware. So it's a very conservative approach, but that's the easiest way because what we have seen in the marketplace is when you go with the latest and greatest, many times things break pretty easily. So they want to go with a true tried method and they stick with it till the GPUs fall off. That's how I've seen it work.
Nice. Now, I mean, we mentioned NVIDIA, we mentioned AMD a couple of times. What do Cisco as a company do differently than the competition, that other vendors, in matter of this AI data center that make it better than the competition?
Yeah, when we think about what makes us better is we have our own compute, we have our own network switches, we have our own controllers, and then we also have our own storage stack in terms of what we do with the storage stack that I'm referring to is we also have great partners with Pure and NetApp, but when it comes to storage on our servers, we have something called the vast storage systems. So these are things that we control and that's within our ecosystem. So the thing that we're able to do better is we're able to validate the integration of all these three elements together and make sure that we are able to deploy, validate, and get the customer on their feet pretty quick, which is probably the greatest strength that we have.
It feels to me like many customers cannot really easily do this themselves due to lack of experience. For many providers or companies, it's their first AI data center, and it's a massive investment and new technologies, probably. We also come in typically with CX services where we send people like you on site for deployment. We help with the design. We benchmark to prove everything is deployed. And then when we leave, everything is working fine. And we also may not necessarily leave at all, right? We may stay hand in hand to provide some services and help the customer operate the data center, where other vendors might just be interested in selling their hardware and software and then not hear too much from the customer from that point on.
Yeah, that is perfectly put, Nico. So our main advantage is it's end to end. It's completely packaged. We do end to end validation and testing for you, and we can go to the level of fine tuning based on the workload that you have. That'll give you the best optimal performance that you can get out of the infrastructure.
I have a future-oriented question to close on this episode. What's the next innovation expected to be? Obviously, AMD and NVIDIA are going to keep releasing stronger and stronger GPUs. We are improving our servers, but where's the bottleneck for now? Are we eagerly waiting for 800 gig Ethernet because the GPUs are already going faster than that to this day?
So today's GPUs, think about it, right? When I talk about uh, a GPU, either AMD can do about 960 gigabytes per second, and NVIDIA has an internal switch called the NV switch, which can probably do 2.2 terabits a second. So as quickly as the networking can scale, the GPUs are also able to scale. Today, the 800 is a great value to have, but we do not have a SerDes that does 800 on a single port. We have to split it into multiple ports, multiple 400 gig ports. That's going to be the bottleneck. Once we solve that, we will be able to use all 800 gigs of throughput from the GPU. So we need an 800 gig NIC, and that'll allow us to work. The second part of this is the networking side is also accelerating. Cisco has 800 gig port switches today, which is based on our G200 Silicon One ASIC. And the P200, I think, also does this. And then what we also have is we're talking about 1.6 terabit switches, which is the Ultra Ethernet Consortium standards. We are accelerating on the networking side as the compute side accelerates. At some point of time, we need to figure out how much a bus can handle, right? We're still talking about a computer, server, my PCIe bus. So what do I do?
Well, Venkat, thank you. That was super interesting. I learned a lot about AI data centers. We're going to put in the show notes the link to the CX services where you belong and where we can offer a lot of services to our customers to help them deploy their data centers. And thank you again, and see you in the next episode.
Thanks, Nico. Thanks, Tristan, for the opportunity. It was a pleasure talking to you guys.
Likewise. Thank you, Venkat.
Thanks. Yep. Bye-bye, guys.
Thanks for listening to this episode of the Cisco Tech Stories podcast. You can subscribe to us on the Cisco Podcast Network in SoundCloud or your favorite podcasting app. You can also find us on our own channel called Cisco Tech Stories in every podcasting application. Thanks.
These sketches, dreams on paper thin, steel and glass where bites begin. A whisper to the future's roar, blueprints drawn, he builds a core. Lightning bolts through circuits race, data floods yet leaves no trace. Venkat, the architect of speed, he gives the world just what we need. Floods of data, GPUs unite. Venkat's facing blazing bright. He threads the cables, seamers flow, a spider spinning webs that glow. No drop, no lag, a perfect stream. Venkat's crown, a coder's dream. Every wire sings his name, the network dances in his flame. Venkat, the architect of speed, he gives the world just what we need. Floods of data, GPUs unite. Venkat's vision blazing bright. Venkat's